Hello, y'all. This is Darrell Lee Berry Jr. back for a quick video. Uh, Let me just move my camera a bit. I've actually uh, took my whole computer out. I don't normally take my laptop around, but today I gave a talk on for extra credit for my modern physics lab on one of my experiments that I did this summer. So I'm actually just making this quick video to talk about that a bit before I go back to writing my paper. So I have one more paper that's due sooner than normal. It's due on Sunday tomorrow because the semester ends, so the professor has to get the grades in. So what I'll do is just show some images from some of my experiments, did five, and just to whet the appetite because what I plan on doing is making some talks about these experiments. That's why I call this one the Flerf Tears sort of edition because, of course, flat earthers in their delusion and ignorance and lies say that scientists just believe and just make up stuff and anybody who's definitely has a physics degree or an astronomy degree know that's absolutely not true. And of course, you don't even need to have a degree to know that. You could just be on the way to a degree. So right now I'm a senior, and this is I guess I don't even know how many labs I've done at this point between all my classes, but this was the most advanced lab. This class was modern physics lab. So things were a lot more open. Like it wasn't like, you know, this lab only does this and you just go through the steps. We got some very in some instances complex data, and we had to basically there's multiple ways to interpret the data and multiple things to address that data. I'll talk about that in a bit when I get into the current experiment I'm doing now. But what I'll do is just talk about these experiments a bit, and perhaps I'll look around and see where I'll get some talks at. Maybe because I gave a talk on dark matter and dark energy on MC Toon's channel, and he welcomed me back, and I said I'd like to go back as well. So maybe I'll go back to his channel and give some presentations on these experiments I did. And probably won't give a full presentation on all of them because, frankly, not every single one I'm very interested in. Like transitions are interesting, but it's not my major field of interest. But that's one of the ones that my lab partner wanted to do. Not in mind doing it was easy to do for a short week. And but most of the other ones we did was pretty interesting. So I'll show some images from those. Like I said, this one will be short. I want to just make sure I get a video in before I go back to writing my paper. And I plan on finishing that paper tonight. My French class started this week, so that's another reason why you haven't seen me as much this week, because this week I've had three summer classes. So summer classes are accelerated by themselves. But then this week is my last week of my modern lab, the first week of my French, and I'm in the middle of my math class, my linear algebra class. So this week was just crazy busy. Uh, with finishing assignments and doing lab work and so on and so forth. So next week I should be able to get back to a normal streaming schedule. I do start as a learning assistant again, which I'm excited about. This will be my second time being a learning assistant. I was a learning assistant in the spring. Before that, I was a tutor, tutored math. So, so basically, the learning assistant is sort of like a mix between a tutor and like a pure coacher. As I help in a class and hold office hours to help the students with understanding homework problems or doing exam practice preparing for the exam for an EM class. This class is going to be EM with a lot of it's a science. It's not like so some of the science classes are only for physics majors or astronomy majors because it goes more in depth. This one is for life science people. So it won't go as in depth into the science, but they have to know at least a little bit of science. Like they have MRI machines and things like that. That's uh, some reason the flat earthers just have this delusion where they divorce things from reality, where they say science is fake or whatever. When things like MRI machines and of course the electricity I'm using now, all of this stuff works on that science. So even the medical doctors have to get some physics in to understand what they're doing. As a matter of fact, one of the talks today, one of the students did uh, some of the principles behind PET scans was where, when they inject people with, maybe you don't know, but I didn't know myself till I saw the talk. Like a PET scan, basically they inject you with an isotope, and the isotope emits some gamma rays that can be picked up by the same kind of scintillating detectors that we use that I'm using in my lab, that I used in the lab this week. And that's how they detect like tumors and things like that. So it's pretty interesting. So the medical people have to know some physics too, how that stuff works. So let me go ahead and bring up the images here. So the first one I did this semester was measuring the speed of light. So the speed of light is very important in astronomy. I'm an astronomy major as well. So of course, astronomy at this point, like we don't, sometimes we could send devices where we're going. Like there's a lunar orbiter, and there's a rover on Mars, and there's a satellite orbiting Mars, and they sent a few satellites to Venus, is my understanding, but it's so hot that it doesn't last long after it lands on the surface. Um, Voyager is on the way out the solar system. We're out the solar system already. But for the most part, when we're studying like different solar systems and things like that, we have to absorb the light that's coming from it. Um, so I'm not aware of anything else we can do. Absorb the light, even when we measure the mass of these things by their revolutions. And maybe I'll make a video about that one day. We still recognize the revolution by seeing a light coming from the object and seeing where it's at. So astronomy is basically interpreting the light that's coming from different things. So that's why I was excited about measuring the speed of light myself. So this is my curve from my experiment. And if you look at the x-axis, it's a change in time. You look at the y-axis, it's a change in distance. Basically, we shot a laser down the hallway and bounced it back with a mirror and measure the difference in time for the signal to go directly to an oscillator, then bouncing off the hallway and coming back down. And the slope of that line gave us the speed of light. So we got pretty close to the official value. We got 2.9 plus a few decimal places, and so yeah, we were within our tolerance level for error. So measure the speed of light. So I'll definitely incorporate that in, like that I measured the circumference of the Earth, and of course we use light to do that by measuring the angle from the sun, and we use radar to get the distance of the sun, and of course that's based upon the speed of light, how long it takes the signal to go there, and how long it takes the signal to come back. So I know that's a valid experiment because I've measured the speed of light myself. So they sent the signal out, take a certain amount of time to get back. So I'll be able to calculate myself how far the sun is, or the moon is, or what have you, by just getting the data of how long it took for the signal to get back and multiplying it by my own value. My value is a bit lower than the official value. Like the official value is like 2.94 and some change. Mine was 2.90, but our error margin was plus or minus what have you, and it fit within the error margin, so it was pretty good. So the next experiment I did was, it was basically verifying that a quantum is a thing. So quantum talks about how uh, matter, electrons, it absorbs and emits energy at discrete frequencies. It's not like a continuum, but these discrete energy levels. So what we're looking at here is one of the tubes, the Frank Hurst tubes, where we send current through some gas and excite it, and we're able to see how the gas excites only at certain discrete levels of energy. And if it's not at that discrete level of energy, then it doesn't excite properly. So basically, if you look at these, might be a bit harder to see there. Oh, we have a question in the chat. Let's see here. It might be about the first one. So this is my modern physics lab. So I'm a student at UT Austin. This is a modern physics lab. So the laboratory deals with things like measuring constants, like we measured the Boltzmann constant, measured the speed of light, like I was just talking about. Um, Other people measured, can't remember all the things that we measured. This is a pin that we get from successfully doing the laboratory. It's called the Heck Lab, yeah, because all of these uh, uh, constants we can measure. Like H is the Planck's constant. We can measure that. We can measure the charge of an electron. Oh, you're in my lab? You at UT as well? Which your professor's name? He just says he's in my lab. That's interesting. So he will respond in a second. I don't think I remember to set the chat thing to instant, so it's taking a little while for his chat to get back, but he replied a bit to let me know who his professor is for his lab. But yes, modern physics lab, we cover a lot of my. Yep, six, awesome, cool, man. Uh, I ain't even know I had a follower from class, so good to see you. How excited are you? Oh, awesome. How did you enjoy the presentation? Today I gave a presentation on my which lab was that? Lab three. So ironically, that was this lab here. So this is actually one of the slides I showed in my presentation where uh, uh, I used a scintillation device to measure the kinetic energy of an electron when it's hit by a high energy gamma ray. And we're able to take that information and plot uh, how the mass of an electron can be measured through its energy, through its kinetic energy, both classically and through relativity. And only through relativity do we properly measure a static mass of an object, because the masses of things don't change because they're going fast. Awesome, thanks, man. Glad you liked it. So I plan on doing the more in-depth talk. If you, I could post a link now, by the way. I gave a talk on dark matter and dark energy on MC Toon's channel. And Yusuf, like I said in the talk, one of the things I do is debate the flat Earth people. And how in depth are you into the topic, or did you just get to my channel because we were in my class, or were you already like into the flat Earth debunk thing? Maybe even saw my talk already, but I'll post a link in case anybody else is looking. Here it is. All right, that came up properly. So here's the link to my dark matter, dark energy talk. So I plan on doing another one like that. Experiments, the ones that I enjoy. Awesome. Well, perfect timing. Normally I would have streamed earlier, but I was actually working on our paper that's due Sunday, and time got away from me. I was like, oh damn, I didn't even stream today. So I was like, well, let me come on and just talk about the labs, and before I go back to writing about the labs. Normally, right now, I would do I'm doing a review of this Veritas documentary, this awesome documentary on flat earthers, but I'm gonna have to miss it today because I got to finish this paper. So, but I wanted to make sure I was on to talk about something. So, but if you check my channel, you'll see like there's a playlist called Flat Earth Debates, and you'll see how I debated a few flat earthers on this debate channel, Modern Day Debate. And I actually talked to a few on their Discord channel, but invariably they start to get rude with me when they realize I'm not going to fall for their nonsense, more or less on different channels. Well, I would have to say probably this one today is probably my favorite one. Simply because I was able to do a lot of stuff by hand. I know I have to get used to doing stuff with coding, but I hate coding. I guess I'm not good at it. But sure, when I get better at it, I'll love it. I'm definitely a lot better at coding now after this class because I had to do it so much. But I had to derive this formula by hand and manually type it into the code. So probably why I enjoyed it a lot because it was doing a lot of by hand math. So yeah, I guess this was my favorite one, the relativity one. I also like the speed of light, like I was saying earlier, just because I'm gonna use it a lot in astronomy, and I'm gonna use it a lot to to display flat Earth stupidity. And and I have to say I do like the quantum one, the quantum nature one here because I don't know. That is if so I plan on going to graduate school for astronomy, but if I did go for physics, pretty sure I will go for quantum stuff. So I just like that. And I thought it was pretty cool seeing the uh the different fluorescences there of the different excitations of the atom. So I thought that was pretty cool. And then how it accelerated the electron was excited and then it slowed down again and accelerated again. So we have the three bands. But I'm going pretty fast on it, but I'll talk about the details another time. But I'll go to the last two experiments before I log off. I talked about that one a bit. So this is probably my least favorite one, talking about favorite, just because I don't know, I'm not really into the like uh, engineering part of things. I know there's people who love engineering, but I can't say I like engineering. But the fact is, I didn't really like being an experimentalist as well until this class made me like it a lot more. It was pretty fun. But suffice it to say, this is for a semiconductor experiment where we was able to experiment with a semiconductor and test the nature of an insulator and a conductor, given the fact that a semiconductor, if you give it enough current or heat it up enough, it pretty much acts like a conductor. So we was able to notice how when the transistor kicked in, when it had enough voltage and the current went up, and we also heated it up to compare the difference. So it was pretty cool. We ended up measuring the Boltzmann constant with that. My measurement was horrible. I didn't get too close. I know we had a bum experiment the first one of our the devices were not working so well, and like the one today, Yusuf, the one who did that experiment said about the temperature, keeping the temperature of that thing straight I'm sure it wasn't user error for him. It just was difficult. We ended up just finding a temperature that it stabilized that and doing our temperature there. But I know it must have been difficult for him to keep moving it back and forth. And then the last one, the experiment that I'm writing about now, was basically we so let me back up. So there's several radioisotopes. One is sodium 22, and basically what happens is the sodium decays and becomes, if I remember right, neon. And when it does that, it emits a positron, turning one of its protons into a neutron. And the positron meets up with an electron and annihilates and turns into two gamma rays, which is a very direct demonstration of E equals mc squared. And I used to say we had to wait about 10 or 15 minutes after changing the DC voltage supply for the temperature to stabilize enough to take a measurement for that tone. Interesting. So I think by the time we figured out how to make the thing work, it was like already Thursday or something. So because the first day we had to draw all our data. The second day we got it to work, but we realized that the current for the was it the forgot the name of the software, VI software, LI software, whatever the software was, it showed a current, and a pico ammeter showed a different current, and it, we didn't know what was going on. But then it was the third day, Wednesday, when Professor told us, "Oh, these machines have been wonky," and he took some off the shelf, and we found the working machine. So Wednesday was the first day we could actually start getting data. So by the time Thursday came, we were just trying to wrap up. So yeah, we didn't even have LabVIEW. That's the software. Yeah, yeah. So we lost like 2 days of experimentation. I think the first day we usually always trying to figure it out, but the second day the machine wasn't working. So that wasn't our best lab for sure. But yeah, I'm pretty sure we got it worked out. The first and second day we could have did more temperature stuff, but we got enough data to make it work. We got enough data to show it happened, and the graphs look good. But we definitely didn't get as much as we wanted. Like we tried to do the nitrogen as well, but that was the first day we had to throw out the whole nitrogen data. But we had enough to get it done. But the guy today who talked about that lab definitely did better than we did on it. So it seems like he got it working immediately. But it was still fun to do. When I do in LA, when I'm in LA for this EM class, at least I can talk about transistors and semiconductors a bit from experience because they talk about that in EM, transistors and conductors and stuff like that. So ironically, when I did research for that lab, I pulled up the textbook for that class that we used in spring that I LA'd for. So it was definitely helpful because I was familiar with it from where things were in that textbook. Oh, hold up. Where did my image control go? I think I lost my image control. Let's see here. Ah, there we go. So this last lab, basically, so the proton, the positron and the electron annihilate. It sends out gamma rays, and basically what we're doing is we're measuring. So basically, the two detectors are situated like so. And if you notice in the image, the gamma rays go at a 180-degree direction from each other because they're conserving momentum. So when you put the detectors on opposite sides of each other, we detect that. But then we rotate one detector so one is still pointing this way, but the other one is to the side. And basically, we're showing that this coincidence rate is consistent by showing that the distribution of coincidences goes down in the Gaussian curve formation when we alter the angle of one of the detectors. So I know I went fast through a lot of these. But like I said, I guess I'm not sure when because the LA thing is going to start soon, probably at the end of August. Like, look for me to have like a presentation on those things, and I'll see if I can give a talk on it again somewhere. And probably will pick three of the experiments. Like I know I'll do the relativity one, the speed of light one, the quantum one. Well, I guess four of them. I'll probably do all of them except the transistor one. So, but cool. But Flerf tears because all of these things, like relativity, try to say that relativity doesn't happen. The speed of light, of course, they think, you know, we can't see, they make up all kinds of crazy stuff. Relativity, speed of light, even though transistor wasn't my favorite one, obviously the flat earthers have no idea about electricity. One of some of them say gravity is electricity. If they understood electricity at all, they would know that's nonsense. So the transistor lab was another way for me to see how electricity works. Um, what relativity one? Um, what's another Flerf tears one? So I guess that's all the main ones. So I guess everything other than, I mean, the transistor one does get it really good for uh, 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 electricity, but speed of light, I'll definitely keep that in mind when it inevitably comes up. I'll be doing more debunks like with dealing with the speed of light, like already measured the circumference of the Earth. I plan on talking more about that distance measurement to the sun. I read that paper recently, and it was I mean, pretty much what I expected it to be. It just sent the signals there and got the signals back, and didn't have any of the problems that the flat earthers imagine themselves to have. And Yusuf said, how do you align the gamma ray trajectories, the angle of your setup? So actually, what happens is, and I had that same question because it seems kind of odd, because looking at that image again, ironically, once you move far enough away from the 180, you're no longer even receiving this. And what happens, the way Professor put it is, so let's say using this image, let's say that the bottom arrow, the bottom gamma ray is one of my detectors. And let's say I'll move the other detector all the way to at a right angle, like where it says the word positron. So it's at a right angle. Well, at that point, I'm not detecting this. What I'm doing is I'm detecting two different events that happen to happen at the same time. What makes the experiment valid is the one that does happen at a 180 degree, that one happens much more often. So basically, the sodium 22 has three different decay schemes. The first decay scheme is the one with the 180 degree. That happens the most often. It's the curve for that one is short. Is only as much energy as a as a electron rest mass, but it happens very often. The next decay happens when after the positron is emitted and the sodium turns into neon, the neon is excited, and the neon de-excites and sends out an even bigger burst of energy. It's like in 1,000 kilo electron volt range. So, excuse me, is in a 1,000 electron volt range, the kilo electron volt range. So when that one emits, it's a whole lot more energy, but it happens a lot less often. So we might catch some of that on the side, for instance, because even that professor says it scatters in such a way where we still might capture that energy. But the thing is, since it happens not as often, when we have the device angled to the side, the counts go down. And the more to the side you bring it, the more you capture less likely emissions. So that's why it ends up being more emissions at the 180 and it goes down at a Gaussian fit because you're catching emissions that happen less and less often. So that's the way that works. So when you do a fit, the 180 is pretty broad and then it goes down from there. So that's the way it works. And that's right. So we look for the more common one first. Like what we do is, and actually, I just actually copied that picture. That's what actually reminded me that I need to do a stream because I sent my lab partner the image and then I downloaded them. So let me actually share this image here, and this will show you what I mean. This is directly from my oscilloscope. So let's see here, right? And this I think is the best one, right? So let me size this thing, and I'll show you what I mean. So this is from the oscilloscope here. So if you look at this, the bottom curve is from the amplifier. So what we do is we trigger off the amplifier, and we make sure that the amplifier is showing. And I didn't actually take it when it's not calibrated, so I guess you can't see it when it's not calibrated, but if it wasn't calibrated properly, you will see this lower curve, this lower blue curve, and you'll also see a tall blue curve, except the lower blue curve is very strong, and a taller blue curve, it like blinks a lot because again, even though that secondary emission is more energy, which makes it taller, it doesn't happen as often, so it's blinking off and on because it's happening less frequently. So what we do is we trigger then off the SEA channel, which is the yellow channel, and then we adjust the window. So what we do is we set the window really low. So it's like basically we have the window open like this, so we capturing all energy, and we raise the window up until the lower curve disappears. And when it disappears, we lower the window down again, and now we still see both of the blue curves. So then we lower the top window, and then the top one, the tall one, disappears. And now the window is set so that only the short one is in the window, which is why it looks like that. So what we're seeing right there is the bottom window has been raised, the top window has been lowered. So now all we capture is the 511 kilo electron volt curve, and now it's tuned to that one. And then that's going to be the one that we pick up the most often. And since the counter is there, the counter is only going to catch it when it happens at the same time. So when we have it at 180 degrees, of course, we're catching it right off. So boom, 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 the counter is constantly catching them at 180. But once we put one of them to the side, it's not going to catch them as often because it'll have to catch two different events that happen at the same time. And that's why the curve ends up being the Gaussian fit. So yeah, it was pretty cool. So this is another one of the ones I really like. And it's also one of the things that'll bring some Flerf tears because some of the Flerfs say, the flat earthers say that electrons don't exist, believe it or not. Oh my gosh. It makes me laugh so much, man. It's amusing. But I do thank flat earthers. I mean, 'cause like I said in class, they make me appreciate science more. They make me get more involved, like I'm doing now, because I have to be more involved to come talk about it. So I actually thank them, man. They help me appreciate science and learning a lot more, so I'm not as ignorant as dumb as them. So I definitely do better in school since I learned about flat earthers than beforehand. So, but also, that's pretty much all I want to do was just give a little talking. As you can see, I'm all shaved up because I did my talk today. Usually I was having some hair. But I'm starting my LA job, so now I'll be shaving every day again or every other day. So you'll see me shaved up again. But for the last few weeks, some of y'all hair everywhere and growing out because I had a month or so where I didn't have to shave as much because I wasn't doing any classes or talks or anything. So now I'm back in class and I'll be doing some more talks soon. So you'll see me shaved up again more. So, but thanks for joining, Yusuf. It's always good to have somebody in the chat to interact with. Next time you see me, holler at me. We could exchange numbers, keep in touch. And I guess I know I'll be in. Some people are talking about being in the classical dynamics class. I know I'll be in that class in the fall if you're in that class. So, but if not, you'll see me around campus. You know what I look like. And of course, you could always catch me here. But also, man, have a good night. And everybody else, thanks for joining. Like, subscribe if you haven't. Share, help me get to 1,000 subscribers by December. That's the goal. And I'll be back a bit more often next week.